I want to tell you about a search that has been running, in one form or another, for 65 years. It has involved some of the largest radio telescopes ever built. It has generated petabytes of data. It has had dedicated funding, dedicated institutions, and dedicated scientists who have spent entire careers on it. It has inspired movies, novels, and at least one very good Jodie Foster film. It is, by any reasonable measure, one of the most sustained and serious scientific searches in human history. It has found nothing. Now, that is not, on its own, a damning statement. Absence of evidence is not evidence of absence. The universe is large. We have searched a very small part of it. The search continues, and the search is worth continuing. But here is the thing that doesn't make it into the press releases. The search was designed in 1959 by two physicists at Cornell, Giuseppe Cacconi and Philip Morrison, who sat down and asked, if an extraterrestrial civilization wanted to communicate with us, what would they use? And their answer, which has shaped the entire field ever since, was radio waves. Narrowband radio waves, at a specific frequency, deliberately transmitted in our direction. That answer made complete sense in 1959. Humans were perfecting radio communications, and during this time period had developed Project Echo, 1959 to 1961, constructed a long-distance wireless communication system, which included a novel tracking horn reflector antenna, a maser preamplifier, and an FM, frequency-modulated demodulator. To get into the weeds for a minute, this low-noise receiver was the first to provide a high-quality long-distance voice circuit via the Echo 1 passive satellite. The system capabilities were later expanded, 1962 to 1963, with transmissions to the Telstar active satellite, made possible by the invention of the solar cell. Further experiments, in 1964, led to the discovery of cosmic background radiation, verifying the Big Bang Theory, which describes the formation of the universe. So, radio was the most sophisticated long-range communication technology we possessed. It was natural, completely, understandably, almost inevitably natural, to assume that any civilization advanced enough to contact us would use the best tool we currently had. The question this episode is asking is whether, 65 years later, that assumption still holds, and what we might be missing if it doesn't. What SETI is actually looking for, and why. Let's be precise about what the search for extraterrestrial intelligence is, and what it is not. SETI is not a single program. It is a collection of methodologies, institutions, and search strategies united by a common goal: finding evidence of technology produced by non-human intelligence. The technical term for what it is looking for is a technosignature, any measurable property that could only be explained as the product of technology. Footnote 1. The original and still dominant methodology is radio. The logic is elegant. Radio waves travel at the speed of light, penetrate interstellar space without significant absorption, and cost relatively little energy to produce at the transmitting end. If you wanted to send a message across interstellar distances and you were working with human-scale physics, radio is a reasonable choice. The specific frequency that Cacconi and Morrison proposed in 1959, 1.42 gigahertz, the frequency at which neutral hydrogen emits radiation, was chosen because any technologically sophisticated civilization would know about it, and a civilization choosing a frequency to broadcast on might plausibly choose a universal landmark. Footnote 2. This is where the assumption starts to show its seams. The argument that any advanced civilization would choose 1.42 gigahertz because it is universally known rests on the prior assumption that the civilization is choosing to broadcast at all, that it has decided to announce its presence, that it has built a transmitter powerful enough to be detectable across interstellar distances, and that it is pointing that transmitter somewhere useful. Each of those assumptions is doing significant work, and none of them are tested. Breakthrough Listen, launched in 2015 with $100 million in funding from Yuri Milner, is the most ambitious SETI program ever undertaken. Its goal is to survey 1 million nearby stars. Footnote 3. In December 2024, a major analysis of Green Bank telescope data covering 2,623 stars, representing 3,165 hours of observation time across frequencies from 1.10 to 11.2 GHz, found no compelling candidates not attributable to radio frequency interference from human technology. 0. After 3,165 hours of listening across nearly 2,500 star systems, the researchers' conclusion was careful and honest. Less than 1% of surveyed stars host transmitters brighter than 0.3 Arecibo radar equivalents broadcasting in our direction. Footnote 4. That is not a failure. It is a data point, but it is also worth sitting with. The Milky Way contains between 100 and 400 billion stars. Footnote 5. Breakthrough Listens 1 million star survey, ambitious as it is, represents somewhere between 0.025% and 0.1% of the galaxy. We have checked a very small neighborhood, but we have checked it thoroughly, and we have heard nothing. And the methodology we used to check it was built on assumptions that were reasonable in 1959, and which the field has been interrogating with increasing rigor ever since. The Kardashev problem. Whose trajectory are we assuming? In 1964, a Soviet astrophysicist named Nikolai Kardashev proposed a classification system for extraterrestrial civilizations that has become the conceptual backbone of most SETI thinking about what we are looking for. The Kardashev scale ranks civilizations by energy consumption. Type 1 controls all the energy available on its planet. Type 2 controls all the energy output of its star. Type 3 controls the energy of its entire galaxy. Footnote 6. The scale is elegant, measurable, and, this is the part worth examining, entirely built on one assumption, that technological civilizations grow by consuming more and more energy. That assumption is a projection. It is a projection from human industrial history, from the coal age to the oil age to the nuclear age, energy consumption going up, civilizational complexity going up alongside it. It is not a law of physics. It is a pattern observed in exactly one civilization across roughly 300 years of industrialization. The critics of the Kardashev scale, and there are now a substantial number of them in the academic literature, make a simple but important point. Humanity, since the 1970s, has not, in fact, continued on the Kardashev trajectory. We have not aggressively colonized space. We have not built megastructures. Progress has increasingly taken informational, digital, and efficiency-focused forms. The smartphone in your pocket is vastly more capable than the room-sized computers of 1964, and it runs on a battery. A truly advanced civilization might evolve toward greater efficiency, subtlety, and miniaturization, not toward consuming the energy output of its star. Footnote 7. This matters for SETI because the most exotic technosignature searches are built on Kardashev assumptions. The Dyson sphere is the canonical example. Freeman Dyson proposed in 1960 that a Type 2 civilization would eventually build a structure enclosing its star to capture all of its energy output. Footnote 8. The waste heat from this structure, infrared radiation leaking out at mid-wavelengths, would be detectable from Earth. This is a real search methodology. The G-infrared survey analyzed mid-infrared data from millions of stars looking for exactly this signature. It found some anomalous infrared excesses. None have held up to scrutiny as genuine Dyson sphere candidates. Footnote 9. The underlying problem is that a Dyson sphere assumes a civilization that wants to consume stellar-scale energy. But a civilization that has solved its energy problems through fusion, through quantum efficiency gains we cannot yet imagine, through approaches that do not scale with consumption, might not need a Dyson sphere. A civilization advanced enough to build one might be advanced enough to not need to. The radio window problem. Are we listening at the right frequency? Back to radio. Even accepting the radio methodology, the search faces a problem that has been growing more acute as our own technology evolves. The universe has a lot of frequencies, and we have mostly been listening to a narrow band of them. The original Cockney-Morrison argument for 1.42 gigahertz, the hydrogen line, was that it was a universal landmark. But there are other universal landmarks. Water's microwave absorption frequency, the hydroxyl radical line at 1.72 gigahertz. The range between these two, the so-called watering hole, named partly for the frequencies and partly for the metaphor of animals gathering at a shared resource, has been the traditional sweet spot for radio SETI. Footnote 2. But the watering hole argument only holds if the transmitting civilization made the same conceptual choice we did. There is no physical law that says a radio-capable civilization would broadcast at 1.42 gigahertz rather than, say, 22 gigahertz or 47 gigahertz or any other frequency accessible to any other landmark in atomic physics. The SETI field has been broadening its frequency coverage in recent years. The 2024 Sardinia Radio Telescope survey specifically targeted higher frequencies precisely because, as its authors noted, an agnostic search cannot assume the transmitter's choice of frequency. Footnote 10. And that is before you consider that radio may not be the medium at all. Optical SETI, looking for powerful laser pulses rather than radio waves, has been a legitimate research program since the 1990s. The argument is that a sufficiently advanced civilization might prefer lasers to radio. Narrower beam, higher information density, less background noise. The SETI project, currently developing all-sky laser monitoring capability, is explicitly designed to cover the territory that radio SETI cannot. Footnote 1. Gravitational wave technosignatures have been proposed in the academic literature. Neutrino-based communication, theoretically possible, practically exotic, has been discussed. Quantum communication channels, which would be invisible to all conventional search methods, have been raised as a possibility. Footnote 11. Each of these is a legitimate extension of the search space. Each of them also rests on a specific assumption about what an advanced civilization would choose to use, which rests on a specific assumption about what an advanced civilization's goals and capabilities look like. The more honest version of the search is what researchers now call agnostic technosignature detection, looking not for specific signals, but for any anomaly that cannot be explained by known natural processes. Footnote 10. It is a harder problem. It is probably the right one. The deepest assumption that they want to talk to us. Here is the assumption underneath all the other assumptions, the one that rarely gets named directly, that an extraterrestrial civilization, if it exists and is technologically advanced, wants to communicate with us. This is not obvious. It is not even particularly likely, if you think about it carefully. Consider what it would take. A civilization capable of producing a detectable technosignature across interstellar distances would be, by definition, vastly older and more capable than we are. Humanity has been technologically sophisticated in the radio transmitting sense for about 100 years. A civilization we could detect would likely be thousands or millions of years ahead of us. The question of whether such a civilization would be interested in contacting a species that has been broadcasting for a century is a little like asking whether you're interested in exchanging messages with a particularly promising colony of ants. This is not a dismissal of the search. It is a reframing of its implicit assumptions. SETI largely assumes that technologically advanced civilizations are communicative, that they broadcast, that they look for each other, that the galaxy is a place where civilizations attempt contact. This assumption is based on exactly one data point, us. We broadcast. We look. We assume others do too. The academic literature has a name for the alternative, the dark forest hypothesis, though it comes in many flavors. Some propose that advanced civilizations go quiet deliberately, either because broadcasting is dangerous, or because they have moved on to communication methods we cannot detect, or because they have simply lost interest in civilizations at our developmental stage. Footnote 12. Some propose that the silence is itself a techno-signature of a kind, that a galaxy without detectable signals is one in which civilizations consistently choose not to produce them, for reasons we cannot yet understand. There's also a more mundane possibility, raised in the context of Episode 2's Ocean World argument, that most life in the galaxy is sealed inside environments where technological development is physically constrained, and the civilizations capable of producing detectable techno-signatures are rarer than the Drake equation's optimistic framing suggests. Intelligence is not rare. Detectable intelligence, intelligence that happens to evolve in an environment that permits fire, metallurgy, atmospheric radio transmission, and the specific chain of technological development that produces electromagnetic signatures, may be considerably rarer. Footnote 13. What agnostic SETI looks like and why it matters. The good news, and there is good news, is that the SETI community has been having this conversation internally for some time, and the field is evolving in response to it. The shift toward agnostic techno-signature searches is real and ongoing. Rather than looking for a specific type of signal at a specific frequency, agnostic searches look for any statistical anomaly in astrophysical data that cannot be explained by known natural processes. Footnote 10. This is harder. Natural processes produce an extraordinary variety of signals, many of which look anomalous until they are understood. The history of radio astronomy is full of signals that were briefly considered SETI candidates before being identified as natural phenomena. Pulsars, most famously, were initially nicknamed LGM, 1 through LGM, 4 little green men, by the team that discovered them in 1967. Footnote 14. But the approach is more honest. It does not assume the transmitter's frequency choice. It does not assume the transmitter is a radio transmitter. It does not assume the civilization is communicating intentionally. It looks for the footprint of technology in the data, whatever form that footprint takes. The Vera Rubin Observatory, currently in operation in Chile, is conducting an all-sky optical survey that will produce an extraordinary volume of time domain data, capturing the brightness of billions of objects repeatedly over years. This dataset is a techno-signature search in waiting. Any sufficiently anomalous pattern of dimming or brightening, artificial in character, inconsistent with known stellar or planetary phenomena, would appear in it. The James Webb Space Telescope, now in its 4th year of full science operations, can characterize exoplanet atmospheres in detail sufficient to identify industrial pollutants, chemical signatures that would only be present if a civilization were actively industrializing a planet. Footnote 15. These are not SETI programs in the traditional sense. They are general-purpose astronomical instruments whose data can be interrogated for techno-signatures as a secondary analysis. This is the direction the field is heading, and it is the right direction. Not because radio SETI is wrong. It is not. And if a civilization is broadcasting on the hydrogen line, we won't be listening. But because the honest version of the search is the one that does not build in assumptions about what an alien civilization looks like, sounds like, or wants. The honest version of the search is the one that starts from what we can observe and asks what natural processes cannot explain, rather than starting from what we would do and asking whether anyone else is doing it. That is a different question. It is a harder question. It may be the question that eventually finds something. So 65 years, petabytes of data, thousands of stars, no confirmed signals. The easy interpretation is, there is nothing out there. The honest interpretation is, we have been looking for ourselves with tools we built to find ourselves at frequencies we chose because they made sense to us, in search of civilizations that want to do what we want to do. That is not nothing. It is a real search conducted seriously with real science behind it. But it is also a search that has been quietly, rigorously interrogating its own assumptions for the last 2 decades, and finding that the assumptions were more constrained than they first appeared. The next generation of SETI is broader, more agnostic, less human. It is looking for anomalies, not signals. Footprints, not voices. Technology, not intention. It may still find nothing. Or it may find something that, under the old methodology, we would have looked straight past. Episode 4, and the final episode of this subseries, goes to the outer edge of what chemistry and physics can actually support. Gas giants, neutron stars, the theoretical limits of what complexity can look like when you remove every constraint we built our biology around. It's a Tuesday. Somewhere in the Milky Way, something may be generating a signal we have not yet thought to look for. That is somehow more exciting than the alternative. There's still a lot of universe left to look at.